In the second module, we are going to be talking about process improvement, as I'd mentioned. In the last lecture, we had discussed more the issue of problem solving, where something had gone wrong. But when we talk about process improvement, we are really talking about making changes to a process even when something has not necessarily gone wrong, but it is more to potentially ward off a future problem, which we'll see very shortly. And when you talk in terms of improvements, there are all kinds of improvements, but broadly speaking, we can divide improvements into three broad categories. The first category is what we'll call small incremental improvements, and these are typically made on a regular basis. It could be on a daily basis, and these kind of improvements, which do not necessarily require any major investment or time or effort or planning, these are things which individual employees themselves or in very small groups can bring about. And more often than not, the changes are typically restricted to one particular area. They do not necessarily require major management intervention, and these are things which are used very often in the context of what people refer to as Kaizen, or continual improvement, in the context of lean or continuous improvement. Then you have the second type of improvement, which is the mid-level type of improvement. I couldn't come up with a better term for it, and I have not seen a term. Maybe there is one out there, and if somebody is familiar with it, please let me know. But a mid-level improvements are things such as a layout change, because now a layout change is something which more often than not we will not do on a daily basis or on a very regular basis, and these changes typically would affect multiple areas. They are not necessarily restricted to one area, and because they affect multiple areas, they will require the involvement of more than one individual and possibly more than one department. As mentioned, they do not necessarily happen as frequently, could require some degree of coordination, if not an actual intervention on the part of management, to ensure that the change is executed correctly and it does not bring about any kind of an interruption to the normal production. And more often than not, these mid-level improvements do require team efforts, because of the fact that multiple areas might be affected as a result of these improvements. The third kind of improvements then are, which would be called large scale improvements or breakthrough improvements, and these are things which take place relatively infrequently, and these are things which are usually initiated by top management. And some of the kinds of these breakthrough improvements could include things like building a new plant, introducing a new product, changing the basic process or the equipment that is used for the purposes of manufacturing, changing an entire, let's say, software that might be used in the plant. Whatever these might be, these affect not just one area or just a few areas, but can typically affect the entire plant, and these are typically also rather expensive and require a significant amount of time to implement as compared to the small incremental improvements or the mid-level improvements. Now, if you compare, this is a little diagram which some of you may have seen in other contexts, but here if you were to plot over time the performance of a system, and what you would see is that when we have a process by which we continually improve the system, what we will see is that the performance of the system builds up very gradually, but nevertheless it is building up so that the performance of the system is improving on a continual basis. But at the same time, we also have the step increases in the performance, which can be brought about either as a result of a mid-level improvement or as a result of a breakthrough or a large-scale improvement. Typically, breakthrough improvements, large-scale improvements, which bring about major step changes to the performance of a system. The Japanese term for this is typically something called kaikaku, whereas the slow, small, incremental changes and improvements that are brought about in the system is what is referred to as Kaizen. Okay, and like I said, some of you might be familiar with the term Kaizen, but Kaikaku is generally one that is slightly less well known. Please excuse me because it's a little warm today outside, and I guess one gets a little dry talking about it. Now, the question that one might ask is, why do we need, why do we need any improvement, including continual improvement? Continual improvement is required, as we will see, I think, in the next lecture, for the purposes of getting our workers involved. Okay, so it is used for the purpose of getting our workers involved, and also to make sure that whatever processes we have set in place do not deteriorate over a period of time. Then the question is, if you've got continual small incremental improvement in place, you can have a company, let's say, that is on this particular path, where if you plot the performance over a period of time, we see a gradual increase in the performance of the company. Now the question is, if you already have the performance of the company improving, and this generally coming at minimal to no expense to the organization, because most of these are very, very small changes in the workplace or the methods that are used in a particular area, then why do we need to have these more expensive, more disruptive type of breakthrough improvements, the kaikakus or the breakthroughs or the large scale improvements? Why are they necessary? Because we are on the path to improving our performance anyway. Well, the reason why this becomes necessary is because if we were to plot these the improvement of our company vis-a-vis a competitor, and what we might see is something which might look such as this. So although we may have a certain rate of improvement, and again the competitor may not be linear, he or she or whatever the company is may also have some step increases as well in the processes, but the rate of change in the performance of our competitor possibly could be significantly larger or would be larger than ours, which means that if we were to probably extrapolate the performance of this competitor and also the performance of our company into the future, at some point in time, given that we do not intervene in the improvement process, if we keep on improving at the same constant rate that we've been improving at, then at some point in time a competitor is going to overtake us. And this is really what had happened with the Japanese vis-a-vis the US auto manufacturers when somewhere through the 70s and definitely into the 80s, what the US companies found was that although way back in the 50s and 60s the Japanese auto manufacturers were significantly behind the US auto industry, and in fact the Japanese learnt a lot from Ford and some of the other US manufacturers, but the Japanese were working on a much steeper trajectory in terms of improved performance, both in terms of improved quality as well as in terms of reduced costs. and the rate at which the US companies, you could sort of replace the our company with the US industries, and you could replace the competitors with, let's say, Japan. And what was happening is the Japanese were increasing at a much faster rate, and the US said, it doesn't matter, I am the champion, I am the one who invented the mass production and the automotive industry. Nobody is going to overtake us, and therefore they really were quite complacent with regard to the oncoming challenge from the Japanese auto manufacturers. And it was only after the Japanese had visibly overtaken the US auto industry somewhere towards the mid to late 70s or early 80s, that is where the US started to actually pay some attention and understand that they needed to do something dramatically different in order to take on the Japanese invasion, if you will, and to maintain or to protect their own domestic turf. So when we talk about processes and process improvements, okay, now most of what we will be talking about over here will largely be about not the continual type of improvement, but more about the mid-level and possibly some of the breakthrough type of improvement. So these are things that would involve more than one area, more than one workstation, and it will involve taking a look at basic processes and looking at the improvement of these basic processes. So here we see an example of a process, which let me try and explain what is happening over here. You have three different manufacturing operations, okay, and in each one of them you have a separate worker who is working independently. There could be one machine in each, or you could have multiple machines. There could be different machines of each type, okay, more machines of each type in each one of these areas. But you have raw materials coming in over here, getting processed on this particular machine, and the finished product from this particular process is, put in this out bin, if you will, from where somebody would need to come and actually transport that material to the next station or the next department or to the next process, where this becomes the input to the next process. The next process, you again have a worker who takes this as the input, works on it, and then converts it into some kind of an output which is sitting over here, which is then waiting to be transported from here to the next process in sequence. And this again is being processed by this operator that you see here and being put into the output, or that is the finished good, which is then taken by the material handler to let's say a finished good warehouse, from where you then dispatch it to a customer. In addition to all of these three people, you have somebody who is like a foreman or a supervisor, who is basically making sure that each one of these people is doing their jobs correctly. You have a scheduler, because that scheduler has to determine what each one of these people will do and determines the priorities of the tasks that each one of them undertakes. You have somebody in quality assurance who basically determines whether or not the product that is being made is of quality, attempts to ensure that the processes and the products that are being produced are in control. And then you have maintenance, in case any of the machines basically go out of whack and needs to be fixed. So you have essentially 1, 2, 3, 4, 5, 6, 7 and then 8 people, and quite obviously the time that would be taken for the purposes of getting this particular job done, because each one of these things is taking place in a batch. So this particular operator will first work on all of these parts as a single batch. When the entire batch is finished on the first process, that whole batch will move to the second operation, and then again you will wait until this batch gets processed and is in its output bin, and from there again it is worked in a batch mode in the third process. So if you really take a look at it, the total time from when we bring in the raw material to the first operation till we are able to take the finished goods, we have the time required to produce one entire batch in the first process, the time required to produce one entire batch in the second, and the time required to produce one entire batch in the third, plus the time that would be required as the delay time, which is when this particular operator has finished this one batch. That is when he will call a material handler to come in and move this material. And generally speaking, in most plants, at least the ones that I've been to, the material handler is not sitting waiting for this job to be finished so that he or she can move the job to the next operation. There's a delay over there. Similarly, there would be a delay over here. Similarly, there would be a delay over here. So the total time that this material would take to complete this entire sequence is going to be quite significant. In addition to the fact that you have a number of other people who are doing the job, which is a very complex task, because trying to schedule three separate operations individually, especially when any one of them could have a problem or there may be a rush job coming through which would require rescheduling what is being done, this task of the scheduler is certainly not an easy task. When something becomes a problem, it is typically found out after an entire batch has been finished, and therefore that again is a job that is not very easily done. And the foreman obviously has difficulty in trying to ensure that everything is going as per the original schedule. Now, if you were to think in terms of a changed configuration, that means this was the earlier configuration that we had, and we go from there to bringing first of all these three people together, so that you do not have a batch process between each one of them. So you have a container of raw materials coming in to the first process or the first operation. This operator takes that material, and each piece that he produces does not go into a bin which until it is filled will not move to the second one, but he hands this each piece as he finishes on this machine to the next operator, or maybe there's a little table that he can place the part on, so that immediately upon completion of a single part you have the second operator accessing and working on that part. Now you see, number one, that there is no batching of the materials between operations, so that time is collapsed. Secondly, what you see is that there is no delay associated with the time required for moving the part between operations that we had in the previous case, because here each part is being directly handed over from one operator to the next. Also, because all three operators are in one area, actually supervision becomes a lot easier. The quality is a much simpler task, simply because anytime there is a problem with a particular part, so let's say there is a problem in one particular piece that the first operator works on and hands over to operator B, immediately operator B will say, I've got a problem with this part, hold your horses, do not work on the next piece until we figure out where the problem is, usually some sort of a issue with the setting on the machine, and so you don't have an entire batch of bad parts produced, and you get immediate feedback when there is a quality issue. Scheduling does not have to take place for each one of the three operations. You need to ensure that you have this particular part which is fed to the first operation, and from that point on this thing works in sequence, so that individual schedules do not have to be given to each one of the three operators. And to a great extent, when you have this kind of a configuration, you also tend to have the workers at least take care of part of their own maintenance of the equipment. May not be the major maintenance, but at least some of the simpler part of the maintenance. So you can see where a lot of times by reconfiguring the basic process, we can bring about a significant amount of improvement in the time that is taken, in the cost, and in the quality of what is being produced. One of the means or one of the ways in which we can bring about significant improvement in a particular process is via the use of what is referred to as a process chart. And very briefly I will introduce you to the concept of a process chart, because one can spend any amount of time talking about process charting and different types of process maps. But a process chart very simply is a graphical technique which identifies the major steps that a particular person performs or a piece goes through. Okay, and it is while that particular piece is being processed or being formed into the final form, which is the finished good. So we try to trace the path either of an individual who is going through this process of converting the input into the output, or we trace the path of the product which is being converted into the finished good. So the process chart maps either the movement of a person or of a product. Generally speaking, and I think I had briefly introduced you to these symbols in the last class, but here is a little bit of a formal introduction. There are some standard symbols that tend to be used in process charting or process mapping. We tend to use a circle to indicate an operation, and an operation is basically any time we do something in terms of adding value. That means changing some physical or chemical form of the product to closely reach or attain the form or the shape of what the final customer wants. A square or a rectangle will be used to denote an inspection operation where we are checking something, testing something, counting something. Those will be those steps will be referred to as inspection and will be denoted by a square or a rectangle. An arrow will denote transportation. An inverted triangle, as we see over here, will denote storage. That means where we store material in inventory. Whereas a D such as this we will use to denote a delay, which is where either a person or a machine or a product waits for something else to happen. The difference between a storage and a delay is that a storage is planned, a delay is not planned. In process charts, the purpose is to visually organize and structure a situation or a problem, but at the same time the process chart does not really provide a solution. So when we say that we are using a process chart, we are really using the process chart more to organize the detail, organize the data, organize the information in a graphical form in such a way that the graphical representation, as we will see shortly, helps us in saying, you know, which are the areas do I need to concentrate on, and which are the areas which if I work on will give me improvements in the process. Okay, and in and of itself the process chart does not suggest or provide a solution, but it helps us arrive at that by providing graphical or visual inputs. the process chart describes the movements with the help of the symbols that we just saw a moment ago. Now this is an example of a process chart, and what you see over here, the activity that is being done is getting beer. So a person, Joe College, is, let's say, sitting on a sofa watching TV, and now his task, the process, is to get beer. Okay, so generally in the process chart what you will define is, number one, who is the person who is being studied, what is the operation itself, and what is the department in which that particular operation is being performed. The date, who the person is who charts it, and so on will also be listed. Then for each one of the steps that we have in the process, we list each step as one line in the process chart. So in this particular instance, the first step is where the person is in storage, because he is sitting on a sofa watching TV, which is basically sitting in storage. It's not a delay, because it's, he wanted to be there. He's not waiting for something to happen. And then the person decides that he is going to get up and go for beer. So what the person does, it's a transportation action or step over here. And next to this you see also the distance that the person has to walk. So let's say this is 17 feet, or so this is 17 feet where the person walks to maybe the fridge or wherever it might be. Now notice that we have not really broken it down into very small sub activities or sub steps, but when he gets to the fridge, his next step is an operation, because he gets the beer, that is, he opens it and opens the fridge and gets the beer bottle or beer can. Then he walks again, and this time he's going to go and get some glasses and an opener. So he has to walk, and he walks 5 feet, and over there he wherever the glasses and the opener are, he spends let's say 0.1 minute. This would be even here when he is doing this operation, the time required for that is given over here, and it's an operation which is to get the glass and the opener. Then the person goes, then he inspects the glass to see is the glass clean. Okay, so an inspection is a square, as we see over here, and this is the time required to do the inspection. He probably realizes that the glass is not clean, so he walks over to the sink and travels a distance of 5 feet. Then he washes the glass, which is an operation, the time taken. Then he, well, that should have been a travel back, okay, because he goes to the sink. I guess he takes the bottle with him, I'm not sure. So he opens the bottle and pours the beer into the glass, which is again an operation which takes him this amount of time. Then he goes back to return the opener to its location, so it's a travel or a transportation. Then he replaces the opener, puts it back to where it was, it's an operation. Then goes to the waste basket, okay, and disposes of the bottle. So this is a transportation and an operation. And finally he walks back the 17 feet that he had come from to the sofa, and of course the next step would have been an operation which is to drink the beer. But you basically get an idea as to how this particular chart depicts the various steps that are required in order to complete this particular process of getting a beer. Now typically what you do is you would look for those places where you have an undue amount of transportation, okay, which you can see with the help of the arrows, okay, and you can possibly highlight those, or where you have too many inspections. Now here you don't have too many inspections, only one. Or if you had too many delays or storages, which again you don't have too many of. So what you would look for is there a way in which I can try and put things closer so that the amount of transportation can be reduced. Okay, so maybe the glasses and the openers can be placed right where the beer is, or very close to where the beer is. Can we make sure that the glasses that are stored are always clean, so that this inspection, going to the sink, washing the glass, etc., can be avoided. Yeah, and if the place where the opener is more convenient, then again the distance that the person has to travel can be reduced, and so on. Okay. This is another form of a process chart, and again I will not go through the details of the chart itself, but in this, and this is the more common way in which a process chart is typically drawn. What you have is, for each step you have the 5 symbols, the operation, transportation, inspection, delay, and the storage, drawn in blank, and depending on whether that particular step is an operation, transportation, etc., you basically darken that particular circle. Okay, what you see over here is, in this particular instance, we have only darkened the operation and the inspections. What that is supposed to indicate is the fact that any other step which could include delays, storage, or transportation are things which we should try and eliminate as far as possible. So in this, all of these steps, we have only 3 operations and 2 inspection stations, okay, or 2 inspection stages. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 steps in this particular process. Let me see what this process is. This is some sort of a office procedure, okay, and you can read through this if you want to. I'm not going to go through the details, but out of 17 steps, only 3 are actually value adding. That means you're doing something that is useful, and 2 of them are inspection. The rest are all delays and transportations. So that would give you a clue in terms of where to focus your attention on and try to improve the particular process. Generally, process charts are done in pairs. So you have a before and you have an after. So this entire sequence of steps for this process has been modified, as you see over here, where it is down to only 6 steps as opposed to the 17 that we had over here. And again, I will leave it to you to read through the individual steps and see how this particular process has been improved. But the idea is that it's a graphical representation of the process, and by graphically representing the process, it highlights the areas for potential improvement, which is what we will try to do when we are working on a particular improvement process. So in a process chart, some of the ways in which we can try to look for improvements is, can I eliminate a step? Okay, is this thing really necessary? If it's not necessary, can I just skip it? Or if there are 2 things that are happening, can I combine? So let's say if I'm walking with something and then I'm going to go over there and open it, can I, while I'm walking, open the thing? Okay, so is it possible for me to combine steps? Can I change the layout so that the amount of transportation is reduced? Can I eliminate any intermediate storage so that the product can be directly transferred from one stage to the next? Can I change the basic sequence itself? And if by changing the sequence, if the distance traveled or the number of steps or whatever it is can be reduced, these are all possible ways in which we can look at the possibility of improvement in the process chart. Another possibility is a flow diagram. A flow diagram is another tool or a technique that can be used to chart what is happening to a particular process, and here the actual flow path over which a product flows is superimposed on the layout of that particular area, and in doing so you basically highlight any unnecessary moves or moves over long distances, any redundant steps and so on. and basically it helps to visualize the problem and the solution. A lot of times what people have found is when they draw things like the flow diagram, is for the first time somebody actually gets an idea in terms of how far and in what kind of ways the material travels. I remember many years ago we had visited Pratt & Whitney, which makes these jet engines for Boeing and other manufacturers, and what they mentioned was that when they actually did their analysis, they realized that their products typically travel something of the order of 7 or 8 miles within their facility before they left as completed products. Okay, and that's, of course, you're talking about jet engines, so you're talking about large parts, but still 7 or 8 miles, I mean, it was an eye-opener even for Pratt & Whitney. So if you were to try and do a simple flow diagramming of some of the of some of your processes in your plant or your operations, you'll find that you might have a significant improvement possible as well. So again, some of the kind of questions that we can ask even in flow diagrams is this particular operation necessary? Can we change the sequence? Can we change the layout? Is it necessary for us to manufacture or do each and every operation? Can we subcontract? Or sometimes when the flow path is very complicated or too long, can we buy another machine to make the thing more simple? This is an example of a flow diagram where you see by flow charting, number one, you identify the distance over which the flow path has to move, and secondly, the sort of loops, okay, that we make a person go through. Sometimes we may have somebody go from here to here, then back from there to there, from here to here. It is quite possible, and this becomes very, very visual. And again, what you'll see is that we have tried to use the same symbols, which are operations, transportation, delay. There are no inspections over here, but not delay, this is storage. Okay, but you can use some of the same graphical symbols that we talked about earlier, but these are useful techniques for the purposes of displaying the information regarding the process.